Right. We've arrived at a place where we've established that we believe that light can be described using a wave model or a particulate model, the photon model under certain circumstances. We've seen now evidence that energy levels exist. The last couple of videos, we've looked at experiments that I will assert leave us no choice but to believe that electrons in atoms can only have certain energies, that they're restricted to a relatively small number of energy levels. Okay. This is a very strange idea, and this was an idea that really troubled people in the chemistry and physics community in the early parts of the 20th century. In order to reconcile these observations or make at least some degree of sense of them, what eventually happened is the origin of what is known as quantum mechanics. Quantum mechanics amounts to saying we're going to take wave ideas and apply them to atoms and electrons. Essentially, it takes what happened to light, where folks thought they understood light as a wave and then decided they had to use this photon model to explain certain things. Essentially, we're going to flip that around and say atoms, electrons, things like that feel like they should be just little tiny particles, that they should act like really small balls or something like that. But in fact, they don't always do that. And for certain things, we're going to have to treat them like waves to be able to explain what's happening. Okay, this idea should trouble you somewhat. It's very non-intuitive. This is one of the more just intellectually difficult pieces of this course. All right, so let's take a look at some things that happen when we do quantum mechanics. The first thing we're going to need to mention in passing is the idea of the uncertainty principle, or Heisenberg's uncertainty principle. Okay, there's lots of ways to express this idea. It's something that happens when you think about things as waves. And what it says, a simple way to say it in words, is that the position and the energy, or the position and the momentum, cannot be specified simultaneously. So if we take an electron in an atom, it says if we were to know where the electron was, then we would lose information about its energy. Flip that around, if we can measure its energy, then we lose information about its position. Okay. In terms of an inequality, that says down here, delta x is, say, the uncertainty in position, right? X is just representing a position here. So delta x says we know it's in some sort of window, right? P here, the P in there is momentum, okay? A little bit of physics notation. And the product of the uncertainties in position and momentum, this says, has to be at least as large as h over 4 pi, right? Bear in mind, h for macroscopic things, h is a very, very small number, right? Because right now it's reasonable if you're thinking like, that doesn't make any sense. I can know like where my car is and how fast it's going at the same time, for example, and indeed you can within a very, very great degree of certainty, right? The problem is that if you're an electron, then your energy or your momentum is much smaller, your size is much smaller, so the scale on which you want to know your position is much smaller, and then this h over 4 pi restriction becomes rather real, right? For something that's macroscopic, the size of a person or a car, saying that there's this infinitesimal uncertainty in these things is of no particular consequence, right? But for electrons, it's going to matter a lot. So because of this idea, this is what leads us to the notion that we treat electrons as delocalized waves when they're bound to atoms, okay? Electrons and atoms cannot only have certain quantized energies. That's the idea of energy levels that we've worked on in the last couple of videos, right? We can measure the electron energy reasonably well, that says, because when I measure the wavelength emitted in a spectrum, for example, I measure the difference in energy between two energy levels, right? When I looked at those photoelectron spectra, I can measure the energy that it took to remove an electron from an atom. That tells me what the energy of that atom was while it was bound to that atom, right? So I can measure the energy. That says I can't measure where the electron is. I can't know its position because I know its energy. That's an uncertainty principle kind of result, right? This leads to the idea that electrons and atoms are always thought of as these delocalized waves. We just described negative charge sort of smeared out in space. This picture over here, this represents the distribution of electron charge, say, in a hydrogen atom. Okay, where the density of the blue dots there represents the amount of negative charge that we might find in that area, or the probability of finding the electron at a particular point. Okay, you can see that it's obviously got more, the electron is more likely to be in a region here kind of close to the nucleus. My origin is the nucleus of the atom, right? But you can also see that out here at relatively large distances, I can still see some of those dots, right? I can still see that every once in a while, my electron, I could think of it as saying it could wander quite far from the nucleus. Okay, so I can't say the electron is here now and it's there later. It's not like on a path like a planet going around a sun or anything like that. It's just this smear of negative charge spread out in space. And again, that idea bothers people. It's not sort of intellectually comfortable. So don't be startled if it feels weird to you. So in order to talk about how we describe these things, we're going to work towards the idea of orbitals, okay? Some of you will remember hearing about orbitals in high school chemistry. Some of you maybe will not. We're going to develop an idea here, and if you did hear about them in high school chemistry, we're going to talk about them at least a bit more mathematically now because, well, you know more math now than you did then, right? And so there's more things I'm allowed to use in explaining how this works. But we're going to start with a simple idea, the idea of a standing wave in a string, okay? So imagine that I have a string, it might be a guitar string, it's got some fixed length, and I'm calling the length of my string here is L, right? So that's the length of my string, and I take my string and I'm going to tack my string down so that the two ends of it are locked in place. Again, if it's a guitar string, that's just where the beginning and ending points are. Those points can't move because they're pulled down onto the guitar, right? And so if I pluck that string, if I just do that, the wave that I would most naturally make would be the one on the bottom, right? Where my string oscillates at either the center of the string rises up, and then if this was watching it in time, it would then go down, it would oscillate back and forth, right? That's a standing wave because it will just keep vibrating in that particular way, right? It's not a traveling wave moving through space, okay? If I were good at playing the guitar, which I'm not, then I could also just place a finger lightly at the midpoint of the string. And if you did that and plucked the string, you could play what the guitarist would call the harmonic or the overtone of that note. When you did that, now my two ends of the string are still not moving. Right? The points that are not moving are sometimes called nodes in the wave. And now I also have a point at the center line that is also not moving, right? Because as this wave oscillates, if I look at it a bit later, it'll be down over here and up over there, but it'll still not have moved at the center point if I could draw better than I can, right? Up above is one that would be challenging to play on the guitar, but in principle exists, which is where we now have added two fixed points along the length of the string, right? So we have a total of four stationary points now in our wave, right? Four places where the wave goes through zero, or four things we could call nodes. All right. It turns out that each one of those things has a different wavelength, right? My wavelength is getting shorter as I climb up that ladder, okay? There is no wave with a wavelength in between the ones that are there that could sustain itself in the string, right? Because suppose I had a wavelength that was just a little bit shorter than the one down here. My wave might go like this, come down, but if it did that, then when it gets here, I'd have to have moved the other end of the string, right? And moving the other end of the string is not allowed because it's physically locked in place, okay? So in this problem, there's only a set of waves that can exist, and they look like the ones that are there, okay? I've put a label over here just to count. N here is counting, let's say, how many half wavelengths are in the length of the string, right? So in my wave on the bottom, the length of the string L is equal to 1/2 of a wavelength. In the N equals 2 wave, the length of the string is equal to a whole wavelength, to 1 wavelength. In the top wave, the length of the string is equal to 3/2 wavelengths, right? Because a wavelength of this wave goes from here to there, and then I've got another half wavelength after that, okay? This symbol over here that I put on the y-axis, that's a Greek letter psi. That is the symbol that we use for what is known as a wave function, basically an equation that describes a wave, okay? So I labeled those to say my string here is mapping out essentially a graph of what that wave function would look like for each of those waves, okay? So let's take that idea and now imagine that I wanted to try and turn those waves and write an equation for them, okay? If I did that, I would see that the equation that can describe all those things, I could build this by putting L, remember L is the length of the string, right? So L is not a variable here. L is something that was set when I picked the string, right? My n up here, this is the n that was labeling my, my different waves. So I'll just call this the label, right? And in those labels, we said it had to be a whole number, right? It could be 1, it could be 2, it could be 3, it could be larger integers than that, but it can't be anything in between. It can't be a fraction, okay? Then there's a pi and there's an x in there. X is just where we are along the x-axis, right? Let me flip back here for a second, right? So if I'm here at this point, x is equal to L over 2, right? Because my axis is going from 0, this is x equals 0. Over here, I've got x equals L. So at the midpoint, I'm at L over 2, right, for what x is. And if you put that in here, you should be able to convince yourself you're evaluating the sine function in radians. That's what leads to the pi being in there, right? This equation would give us, would match what those waves look like, okay? So in the case that n equals 1, for example, as x goes from 0 to L, I get a half of a wavelength of a sine function because my argument goes from 0 to pi, right? For n equals 2, if n equals 2, for that case, I get still x goes from 0 up to L, right? So as that happens, what happens to the argument of the sine function? It goes from, that means n pi x over L goes from 0 up to 2 pi. Right? And if you keep doing that for all the different n's, you'll see that it always works, okay? This n that just inserted itself into that equation to make it general to apply to all of them, that's an example of what we call a quantum number, okay? It's a thing that labels the allowed solutions to a problem. In this case, think about what made it possible that we could only have these few waves, okay? The thing that makes only these waves be possible is the fact that I put a rule on the system. I said the two ends of the string could not move, right? In mathematical terms, if we want to be fancy about it, that says I put a boundary condition on my system. I said that at x equals 0 and x equals L, I can't move the string. Okay, if I hadn't done that, then I could have had any wavelength whatsoever, right? Because there'd be no rule that said I couldn't have the end of the string moving up and down, and then I wouldn't have to worry about that, right? So my quantum number comes because I put this constraint on the system that said I couldn't move the ends of the string. So that's what a quantum number is. We talk about atoms, we're going to have a larger number of quantum numbers, and they're going to feel weird, but they're not coming from magic. They're just coming from doing math, okay? A little bit of just some details of how we work with these things. If I wanted to talk about these waves, like if these were sound waves, say, and I wanted to talk about like what does it sound like? How loud is the sound at different places in my standing wave, for example? The way to do that would be to take my wave function psi and square it. So now I have on my y-axis psi squared. When I do that, essentially it just takes my sine waves and it makes them, they get to be positive everywhere, right? Because I'm squaring the number where before as the wave itself, it goes positive and negative. The intensity of the sound, the loudness, the volume, that couldn't be negative anywhere, right? So this corrects for that, and it gets us the right answer for what would happen. So the intensity at any point is proportional to the square of the amplitude of the wave. That's what we've done here by taking psi squared, because psi, that wave function, just maps out this is what the wave looks like. It tells me where is my y value at each point, okay? What does that mean for electrons, for orbitals? It means psi squared is the thing we're going to look at. We want to see like where are the places the electron is most likely to be. Okay, that little picture with the blue dots there at the beginning, that was in some sense a plot of what psi squared, the square of the wave function, would look like for a hydrogen atom. All right, this is, of all the classes in the semester, the one that has kind of the most frightening mathematics in it, but don't be alarmed. We're not going to expect you to actually work with these things. I do like kind of explaining where some of this stuff comes from. Some of you in the past in high school might have been told, well, there's s orbitals and p orbitals and stuff like that, and shown pictures of what they look like, but you were probably told that they just kind of came about in ways that you couldn't understand. I don't like to do that, and so the fact is you do now know enough math to be able to, at some level, understand what's happening. And so that's what we're going to do. This equation is the simplest way to write what is known as the Schrödinger equation. Erwin Schrödinger was one of the sort of introducers of the idea of quantum mechanics, and his name attaches to this equation. In this form, it looks kind of simple, right? It says h psi equals e psi. in actuality, this is a semi-complicated differential equation, just kind of hidden in there, right? It's hidden in there because this hat on the H there, some of you may be familiar with that notation. That means that H there is an operator. What that means is it's got a bunch of things in there that says take all these things and do them to the function psi, okay? When I have that operator act on the function psi, it has to give me back the same function multiplied by e, where e is just a constant. Okay, this is in mathematical terms. If you're a little bit ahead of some of your classmates in math, you might recognize this as being what's called an eigenvalue equation. Okay, if that word means nothing to you, don't be alarmed about it. Okay. But this thing says H is going to tell us what's the energy, right? So my wave function describes an electron, and E is going to be the energy of that electron. H, therefore, must have some things in it that account for the kinetic and potential energies, because those are the two kinds of energies my electron could have, right? So if I take that H and actually expand it to show what it looks like, I'll get one of my frightening equations for the day, which is this one, okay? So this says to do that for a hydrogen atom, this is what my H would look like, is all this stuff. Okay, do you have to memorize that or know that? Oh gosh, no. But just look at what it says, okay? The vast majority of you can recognize the idea that it's taking the second derivative of my wave function, right? So this says I've got the second derivative with respect to x, with respect to y, with respect to z, right? And so I'm going to take the second derivative of the wave function. Here, I'm going to take the wave function and I'm going to just multiply it by this stuff. E is the charge on the electron, 4 and pi are just numbers. Epsilon naught is also just a number. It's a number called the permittivity constant, right? And r here is the distance the electron is away from the origin, right? So my r there, I could replace that with something like square root of x squared plus y squared plus z squared if I wanted to make this look even worse, okay? I do all that stuff and I have to get back the same function, right? Psi, the wave function that I started with, has to pop back out of here, right? That actually should give you some clues about what kinds of functions could show up in here. We need something that we can take the second derivative of and get that same function back again, right? That tells us, if you're thinking about this for even a second, a lot of you probably realize that means the kinds of functions that are going to show up in there are going to include sine functions and exponential functions, right? Because if I take the derivative of those twice, I still take the derivative of sine twice, I get back to having a sine function. Take the derivative of an exponential twice, and I get back to having the original exponential, okay? And so those are examples of functions that are going to work being in this wave function. And we'll see that because I'm going to show you what some of the wave functions look like before we finish up here, okay? I should say one more thing about this. If I went for an atom that was more complicated than hydrogen, my equation would get worse looking all the time, right? Because this thing, with a hydrogen atom, what do I have? I have a proton and I have an electron, okay? So I only have one thing to worry about. That's the energy of attraction between the proton and the electron. If I went to helium, I'd have 2 electrons, and then I'd have 2 things being attracted to the nucleus, but I'd also have the 2 electrons pushing each other apart. So I'd get even more pieces to put in there. My equation gets pretty horrible pretty fast. This is for the, again, somewhat for the mathier people, but it says, if I want to solve this equation, and I'm going to show you some solutions to it, the smart thing to do is to do it in spherical coordinates. Why is that? It's because, well, we expect the atom to be essentially spherical, right? We expect the atom to be more like a ball than like a cylinder or a plane or anything like that. And so if I have a spherical system that I want to look at, using spherical coordinates will, in the end, make the problem simpler. Right, so these are the spherical polar coordinate system, which again, I suspect most of you have seen in math classes. It says we still have 3 variables. Right now, our 3 variables, instead of being x, y, and z, are going to be r, theta, and phi. R is the distance from the electron is away from the proton. Right. Remember, the electron is, gosh, like 10,000 times lighter than the proton. And so we think of the proton as being just standing still. It's the origin, and the electron is swirling about it, okay? That's fancy. If we want to say that fancier, we can say we think about the problem in the center of mass system, where we're looking at the center of mass of the atom, and that's essentially the nucleus, okay? It's handy that r is one of my variables here, because my potential energy depends only on r, right? Depends only on the distance my negative charge is away from the positive charge. Because I have a 3-dimensional problem here, I'm going to get 3 quantum numbers when I'm done with this thing, okay? I'm just going to put that out there. When I did the string problem, that was a 1-dimensional problem. We got 1 quantum number, okay? If I had done a 2-dimensional analog of that. Instead of a guitar string, then I would have to think of it as being like a drum head. But then I would get two-dimensional standing waves, and I would get two quantum numbers that would show up in there. When I get to 3 dimensions, I'm going to get 3 quantum numbers that pop out in my solution to this. Okay, so those are the variables that will be in the things when I show actual solutions. Let's look at how those 3 quantum numbers are going to behave, because this is largely the take-home lesson from this, right? The quantum numbers, they're referred to in symbols as n, l, and m sub l. In words, they are sometimes called the principal, azimuthal, and magnetic quantum numbers. I generally don't refer to them by the names because it just makes this even more confusing, and frankly, it's confusing enough already, right? But if you see those names, they're mostly historical, but they refer, the principal is n, so they're in the same order there. If I know all 3 of those numbers, then I've defined what we call an orbital. Okay, an orbital is the wave depiction of an electron in an atom, or a place where we could think of an electron as being in an atom. Okay, and so what we're going to work towards now is building up what kinds of orbitals can we have based on the rules that govern these numbers, right? Remember, in my string problem, my quantum number had rules. It had to be a positive integer, right? And could be 1, 2, or 3, but it couldn't be 1.5. It couldn't be 0, because then I just wouldn't have a wave at all. And so I had, the way my equation worked, I needed to have n be an integer. Okay, so let's see what the rules are for these quantum numbers. I'm essentially just going to tell you what the rules are, because the math of coming up with them is a bit over our heads at this point. So n is my principal quantum number. It is gonna largely determine the energy and the size of an orbital. Okay, the things when we talk about shells, we're typically mainly thinking about going up in n value. Okay, the n quantum number has values that are just like the n in the string problem. It starts at 1 and goes up in whole number increments. So it can be 1, 2, 3, and in principle, it could go as high as it wants to from there. Okay. L is known as the azimuthal quantum number. I try in the slides to always write my L's as script L's so that you can tell the difference between an L and a 1 and things like that, okay? If you're ever like taking notes, try to be careful that you make your L's distinguishable. Otherwise, it could be really weird looking, because you could get something like this that would look like it said 1 equals 0, okay? That L quantum number largely drives the shape of the orbital, okay? It has a little bit to do with its energy, but mostly it determines its shape and sort of what it would look like if it was a thing we could see. It gets a little complicated because the allowed values of L are that it starts at 0 and it can go up as high as n minus 1. So the bigger n is, the more possible L's I'm going to get. This we will come to see is largely responsible for how the periodic table looks, and why, as we go down deeper into the periodic table, we get more elements showing up in a row. So those are the first 2 numbers, n and l, and the rules for them. M sub l, the so-called magnetic quantum number, that one essentially dictates what direction is my orbital pointing, its orientation in space. And the m sub l value is governed by the l value, and m sub l takes on quantities from minus l up through 0 up to plus l, okay? So there are always 2l plus 1 possible values, because there are L values on the positive side, L values on the negative side, and 0 in the middle. If we combine these rules, they'll let us see what orbitals are allowed, okay? And how do they come, what do we call them? Again, it's possible to go in through that equation and just essentially prove that the way to get solutions is to say there are things that follow these rules for the numbers. Doing that requires more mathematical savvy than all but maybe a very few of you have at this point. And so we're not going to try and venture into that part of things. All right, what I'm going to do here is I'm going to work out what are the allowed values for the first few orbitals, okay? So if I start with doing n first, I have to start by setting a value for n, because n tells me what L is allowed to be, and then L tells me what m sub L is allowed to be. So I start with n equals 1, because that's the smallest value of n, right? My L value, L starts at 0 and goes up to n minus 1. Well, in this case, that says I can only have L equals 0, right? Because n minus 1 is 0, so there's no other allowed value of L. Then I can do m sub L. M sub L goes from minus L through 0 up to plus L, but in this case, those are all zeros, so I get only one possible combination for n equals 1, okay? That says I get one orbital, just one orbital because there's one combination. That orbital gets a name. We call that one the 1s orbital, okay? I will tell you that the 1 in 1s comes from the fact that n equals 1. The s comes from the fact that L equals 0. When I write out a couple more of these, I'll write out the sort of naming key for the letters. Suppose I go to n equals 2. Now it's more interesting. I could still have L equals 0. And if I have L equals 0, I still have to have m sub L equals 0. So that's one more orbital. And that one's name is 2s, because n equals 2 now, L still equals 0. But now for n equals 2, I could also have L equals 1, okay? Because L, remember, is allowed to go up as big as n minus 1. N minus 1 is now 1, so that's allowed. That means m sub L, when L is 1, m sub L could be minus 1, it could be 0, or it could be plus 1. So that gives me 3 more orbitals. And those 3 orbitals are referred to as a set of 2p orbitals, okay? So let me write over here, just say this is L, and this is what kind of orbital we get. And if L is 0, I get an s orbital. If L is 1, I get a p orbital. If L is 2, I get a d orbital. We probably won't get past there, but if L is 3, I get an f orbital. And if L is bigger than that, it goes alphabetically after that point, okay? So I would go to G and H and so on for that, okay? There are no known elements that in their normal or so-called ground state have electrons in orbitals that go higher than f orbitals, but those orbitals do exist. They're just usually empty. I'll do one more set here. I'll do L equals 3. First of all, I get the same things as above. So I still, n equals 3 rather. I get L equals 0, m sub L equals 0. I get L equals 1. And then I get m sub L equals minus 1, 0, plus 1. Okay, so this is 1 orbital and 3 orbitals again. And this is now 3s and 3p. And now I have another possibility, because with n equals 3, I could go up to L equals 2. That'll give me m sub L going from minus 2, minus 1, 0, plus 1, or plus 2. So that's 5 more orbitals. And those collectively would be called a set of 3d orbitals, according to my chart up there. Okay. If we keep going, every time we get to a new value of n, we're going to grow one more letter down our chart, right? So if I did n equals 4, I'm going to have 4d, and then I'm also going to get 4f, because then I'm going to be allowed to go up to 3 on my L quantum number. Okay, so this is kind of the origin of where those orbital names come from. And we say, you may have probably were told things in high school like, well, there's 2p orbitals, but there's not 1p orbitals, right? This is kind of the origin of how those things come about. I think I have a cleaned up version of this here coming up. Yeah, so this one, oh, I missed an L there. The L here, this is my L quantum number, the one I've been writing as script L everywhere else for that, okay? This is the possibilities for the ones I just wrote out, okay? And you can see that s orbitals always come in sets of 1, right? Every time it says it's an s orbital, there's just one of those. P orbitals come in sets of 3. D orbitals always come in sets of 5. If we went for F orbitals, they come in sets of 7. It's always going to be an odd number there, because it's the fact that I have 2L plus 1 possible values for the M sub L number, right? And 2L plus 1 is always an odd number, given that L is an integer. Okay, so those are the first reasonable number of orbitals that exist. Okay, and if you remember seeing things like electron configurations that we'll take up in the next video, this is where those orbitals come from that you are filling in with electrons when you write those. Oh, I forgot this was coming. I would have done something dramatic to introduce it. So don't be alarmed by this slide, okay? Don't try and memorize them. Don't even like react to them. Don't be freaked out by it, but do look at them. These are the wave functions for the n equals 2 set of orbitals, okay? The 2s orbital on top, and then the 3 different 2p orbitals here are labeled with x, y, and z subscripts on them, which we'll eventually sort of understand why that is. What's going on in here? A is a constant. It is the so-called Bohr radius. It's equal to about 53 picometers or something like that. And then let's just look at what kind of functions I have in here, right? In the s orbital, I have, this is a function of r, right? I don't have any thetas and phis in here, right? Remember, my variables these are all functions of r, theta, and phi. So the first thing you see if you look at the 2s orbital here is that of those variables, only r appears in there, right? And so that should tell you something. If you think about polar coordinates, if the angles don't matter, that means that this orbital is spherical. Right? Because otherwise there'd be some directionality to it. Right now, it only cares about the distance away from the nucleus. It doesn't care about direction. That makes it round, okay? It's got an exponential piece here and it's got an r over there, right? But that exponential is one of the things we said could show up in here because we'd get it back if we did a second derivative. When I get to the p orbitals, I've got things that now have, this one has just theta in it, the other two have thetas and phis in them, right? So those have directionality, right? If you're really good at looking at functions in polar coordinates and telling what they look like, you might be able to recognize that those three different p orbitals are all perpendicular to each other. That's why they're labeled as x, y, and z here, right? Because if one of them is pointing in this direction, then one of them's going that way, and the other one is going in the in and out direction to match that, okay? And those angles, again, if we were good at plotting things in these coordinates, we'd be able to see that those are three things that are all perpendicular to each other, okay? Again, I don't want you to get bothered by those. I certainly don't want you to try and memorize them or anything like that. But I want you to recognize that they just have normal functions in them, right? There's exponentials in them there. This exp, that just means e to that stuff here, right? So there's an exponential term, there's some sines and cosines. That's really all there is to it. And then there's some constants, right? So there's nothing that's just like totally foreign to you there. It is just a relatively complicated assembly of things that you see all the time in your math class, okay? That's what orbitals are, basically. Those functions define what it means when we say we're talking about a 2s orbital. That thing tells us everything there is to know about what a 2s orbital might look like.